Hello everyone, welcome to this set of lectures, and in this set of video lectures we'll be discussing about noise. So noise is a random source of interference. So we can define noise as a random source of interference, and this noise actually limits the minimum signal level that a circuit can process with acceptable quality. So that is another important thing. This noise limits the minimum signal level that a circuit can process with acceptable quality. So since this random source of interference is limiting the minimum signal level that a circuit can process with acceptable quality, we would like to study about noise. And one another reason, so if I ask question, why to study noise, especially in integrated circuits, the answer would be, if you remember, in the previous lectures when we discussed about analog design octagon, where we discussed about the multidimensional trade-off problem, noise is one parameter in the octagon, and usually this noise trades with power dissipation, speed, as well as non-linearity. So noise is a trade-off parameter which trades with power dissipation, speed, and linearity. Now before starting the discussion, one thing we should understand, in all the amplifier discussion what we have done is we were considering a signal as the input to the amplifier, and that signal in all the cases what we have considered is a deterministic signal. When I say a voltage or a current signal, what we are discussing is a deterministic signal. And a deterministic, the characteristics of a deterministic signal is the instantaneous values, the values at any time instant, is significant, or we can say there are amplitude values for such. We'll always write about the amplitude value of such a deterministic signal. But now when we talk about noise, as we introduce noise as a random source of interference, the signal is, so this is your deterministic signal. This is a deterministic signal. So you'll understand the representation and the other details of deterministic and random signal. Now when we talk about noise, noise is a random signal. So when I say random signal, we can represent it like some variation, we don't know, some variation, and definitely if I represent as t and x of t, it's a function of t. But when you compare a deterministic and a random signal, in a deterministic signal, instantaneous values are important, or amplitude levels are important. But in the case of a random signal, the instantaneous values or amplitude values are unknown, or I can say it is not important. Why I say it is not important is, for example, we will consider. So, for example, let's say I'm considering a resistor. I'm considering a resistor, and and I'm trying to measure the current through, say I have two resistors of same value, say value is R, and I have another resistance, value is R, same value resistors, and I'm trying to measure the current flowing through this resistor, and if you do that, we'll come to know that even though they are same resistors, the current values shown by those two resistors will be definitely different. There will be some difference. When I say difference, measuring current through two same value of resistors are uncorrelated. So why I am telling it is uncorrelated is because because of this noise. I would say a resistor is a noisy component. We'll come to the details of that. And because of that, if I measure the current through two same value resistors, the current values will be different. Or you can think about this. If I measure the current through the resistor, say at time t1, and after that at another time t2, if I'm measuring the current, I would say both will be different, or both will be uncorrelated. When I say measuring the current, what I'm trying to measure is actually the noise component of that. So what we can conclude here is, when I look at noise as a random signal, the instantaneous values are not important, or amplitude values are unknown, or there is no correlation between the measurement of a noisy signal over a period of time, or with the same components at same components. If we measure also, there is no correlation. So we need some form of representation to this noise. So the point here is, how will we represent noise? For a deterministic signal, definitely we can write x of t is equal to the amplitude. Say the amplitude, if it is a, we can write it as a sin omega t or a cos omega t. This kind of representation we can give. But how to represent or how to quantify noisy signal? Yeah, so the point of discussion here is how to quantify or how to represent noise as we represent a deterministic signal. So since it is amplitude values or instantaneous values are unknown, we usually use a statistical representation. And when I say statistical representation, it is given by, or we use average power. Instead of measuring, or instead of specifying the instantaneous value, we always represent the average power. And statistical representation is average power. And if you look at any random process can be quantified by either power spectral density, or another form of representation is mean square value or root mean square value, RMS value. So statistical representation is nothing but representing average power, and in two ways we'll quantify or we'll represent that. One is in terms of power spectral density, other is in terms of mean square value or root mean square value. Now in communication systems, and we would have studied, if x of t is a signal, a random signal, the power spectral density of this is represented as sx, right? Sx or sx of f. This is the representation what we use. Now since we are discussing noise in electronic circuits, we will represent power spectral density as S, and with a subscript of Vn or SIN, where SVN represent the noise of a voltage signal and voltage noise, and SIN represent current noise. And when we say power spectral density, it is always measured for unit hertz bandwidth. So these are the two forms of representation. So the first thing is statistical representation is what we use to represent random signal, and when we say statistical representation, it is average power, and we'll quantify in two ways. One is power spectral density and other is mean square value. Now power spectral density is denoted by SVN or SIN. At the same time, mean square value is denoted by either Vn square bar or In square bar. representing both voltage and current noise. If it is RMS value, it is root of Vn square bar or root of In square bar, and both are expressed over this is expressed over a range of bandwidth. Mean square value is expressed over a range of bandwidth. Right. Now one more thing. So as we told, average power of any signal is represented as limit t tends to infinity 1 by t integral minus t by 2 to t by 2 x square of t dt, where this x of t is actually in this case we are considering as a voltage quantity. And usually this average power is expressed in volt square. The unit is most of the time we will express in V square, that is a unit. And one more observation, what we can that is that is the average power representation of any signal x of t. And one more small information, this is regarding spectrum. When we say spectrum or when we say power spectrum, it is actually the average power carried by noise or the noisy signal at all frequencies. All the definitions are with respect to noise. And here power spectral density is a very important tool in analyzing the effect of noise. And one more relation I need to bring from what we have learned in communication system. If you have a system, a system transfer function is represented as h of f, and input is x of f and output is y of f, or I'll represent the input power spectral density as x of f and output power spectral density as s y of f. This output is related to input by this relation x of f into mod hf the whole square. This relation is also very important. We'll be using this to understand or to represent noise. And one more last thing for this lecture, we discussed about power spectral density and mean square value. Power spectral density is expressed in volt square per hertz as well as mean square value. Now this is expressed in volt square. So if I write this, so I can always write Vn square bar, which is nothing but mean square value. It can be written as power spectral density multiplied by the bandwidth. See, power spectral density is actually the power in a unit hertz bandwidth. Now, if that power multiplied by the entire bandwidth will give you the mean square value. So this relation is also very important. So we started our lecture by discussing noise as a random source of interference, and noise is a random signal. For random signal, the representation is statistical representation, and we will represent average power. Now it can be quantified with two parameters. One is power spectral density and other is mean square value. And power spectral density is measured in unit hertz bandwidth, and mean square value is measured over a range of bandwidth. So the relation between power spectral density and mean square value is Vn square is equal to Svn into bandwidth, and output power spectral density and input power spectral density is related through this expression. So we'll continue in next lecture. Thank you.